Okay, so I think let me share my screen. Is it visible?
Yes, sir.
Okay, thank you. So, in the last class, we will looked at private key cryptography, or symmetric cryptography, where the encryption rule and decryption rule was, the encryption key and decryption key was same basically, right? Now we are looking at what is known as public key cryptography. So I think you might have seen one such crypto system in your discrete math class, which is 1 minute. So which is RSA Crypto System, right? So you might have seen it. In fact, now we are going to look at a couple of crypto systems, especially first RSA Crypto System. And since you know this, so we will cover few basics and then we'll jump into the crypto system and then we analyze it, because I think that part was not there in the discrete math class. Okay, so public key crypto system. Public key crypto system. I will denote it by shorthand PKC, public key crypto system. Okay, PKC. So, the idea of public key crypto system, actually, there was James Ellis, in the British government secret services. So this organization is known as GCHQ, Britain. Okay. So in 1970, he talked about public key crypto systems, but this was an internal document, internal secure document, and it was not known to public. Okay. So where they developed this public key crypto system, but so independently, Def and Hellman, this is a very famous, public key exchange problem, in 1976. Def and Hellman actually proposed public key exchange problem. So this was, uh, so basically, crypto system can be built based on public key and private key. This was a nice idea. And soon after publication of this paper in 1977, Rivest, Shamir, and Edelman, they discovered RSA crypto system, and they formed a company, and now everything is a history. So RSA crypto system is basically based on factoring, uh, large integers. So this is something that you know already, but anyway, we will talk about these things. We'll talk about a couple of algorithms as well. So this was in 1977. Uh, Also, another public key crypto system that was pretty common, and I think we are going to discuss this, is Elgable crypto system. This is also public key crypto system, and actually its variants known as elliptic curve crypto system. We will talk about it also. Very beautiful subject, You can see that how ideas from pure mathematics can develop into beautiful crypto systems, and this is based on discrete log problem. I'll talk about it in details. What is discrete log problem? Okay. So let me first give you some explanation. You know, in fact, we have this private key crypto system, which is symmetric key cryptography. So normally, so what happens? We send, we encrypt messages using private key. Okay, and since public key crypto systems are slow as compared to symmetric key cryptography, so what we do, we use a hybrid approach. So suppose you want to send a message, Alice want to send a message to Bob. So then Alice will use symmetrically, to encrypt the message, and then to send the message, to send the key actually using some key, right? And then to send the key actually, he or she will use this, she will use this public key cryptography. So this approach is known as hybrid cryptography. So let me explain what is hybrid cryptography. So basically, first of all, in terms of keys, what we have. So let me describe in terms of key what we have. Symmetric key cryptography. Okay. What is symmetric key cryptography? I'll denote it by SKC, symmetric key cryptography, or secret key. So Alice is there, the popular character, and Bob is there. And suppose there is a secret key, K is there. So then there is an encryption rule, EK, and there is a decryption rule, DK. Okay. So normally in symmetric key crypto system, DK is either EK or derived from it, So this rule is dependent on the encryption actually. And exposure of either EK or DK will make system insecure, right? Because this is how the symmetric key crypto system is. We are dependent on these keys actually. Okay. So in public key crypto system, what happens now? In PKC, so given EK encryption rule, EK, okay. So EK is we make it as a public key, and DK or decryption rule as a private key. And it is computationally infeasible to determine DK given EK. Okay. Okay. So basically, PKC are used to encrypt short keys that we use in symmetric key cryptography. Okay. So we encrypt data. We encrypt data using, for example, AES, Advanced Encryption Standards. We talked about it. Then encrypt the AES key using public key cryptography. Okay, so this is the approach of what is known as hybrid key cryptography. So let me actually precisely say what is hybrid key cryptography? Or hybrid crypto system, I would say. Yeah. Okay. So what happens? It's a two-step process. Alice first choose a key L for symmetric key cryptography and compute y is equal to EL of x. X was your message, EL is your encryption rule, okay, which is based on the key L. Second, Alice then encrypt L using Bob's public key. This is a difference now. I'll call it EK Bob for public key cryptography, so basically obtaining Z is equal to EK Bob of L. So Y is our encrypted cipher and Z is our encrypted key. So basically now cipher text Y and encrypted key Z is transmitted to Bob, right? So at the receiving end, so what Bob will do, so so this is, remember, so Y is your encrypted text, Z is your encrypted key, both are sent. Now what Bob will do first, Bob first decrypt Z. Z is what? Encrypted key using his private key. Okay, I can call it as DK Bob. And then he will obtain L is equal to DK Bob of Z. Okay. So from encrypted key, Bob has obtained the actual key which is used to encrypt the message. Then second, space. Okay. So now second step, what Bob will do, use L, because now L is known to Bob, right? Use L, to decrypt Y. So he will be obtaining X is equal to DL of Y. Okay. So this is how Bob will receive the message, right? So this is a hybrid cryptography. Okay. Now one thing to note that PKC, I'm just mentioning it, and I think probably I'll ask you to note that public key cryptography never provide unconditional security. Okay, it will never provide unconditional security. So the question is why? Just think about it. So normally we study computational security. Of public key cryptography. Okay, so this is basically a general scenario. You can also think of public key crypto system as a trapdoor one-way function. So trying to give you an example. So that means basically EK should be easy to compute. Okay, EK should be easy to compute, and computing the inverse should be hard. Okay, so this portion should be hard for anyone other than Bob. Bob should be able to do it, otherwise there will be a problem anyway. Okay, so as an example, let me give you one such one-way function. You know, if P and Q are large prime, numbers, you compute n is equal to P into Q, and suppose B is a positive integer, right? The function f from integer modulo n to integer modulo n, integer modulo n to integer modulo n, defined as f of x is equal to x raised to power b mod n. So if GCD of b and phi of n is 1, this is known as RSA encryption function. Okay, so we'll talk about it in more details. So, so I think so. Before giving you in details about RSA encryption, RSA crypto system, though I think you may be remembering few basic things from your discrete math class, but I am going to give you much more details now. So let me build some number theoretic concepts which are important here now. So first of all, Zn is a set of integer modulo, or I would say ring of integers modulo n. Okay. Note that B belongs to Zn. This you have already seen has inverse. Any element in Zn has an inverse if and only if GCD of B and n is 1, right? Only those elements in Zn has an inverse. For example, in Z4, 2 and 3 have inverse. Not sorry, not true. 1 and 3 has inverse, right? Okay. You also remember number of positive integers less than n and are relatively prime to n. This number is phi of an Euler-Torsion function, if you remember. Okay. So if we denote Zn star. Zn star, all those A mod n such that GCD of A and n is 1. So basically I am looking at set of residues mod n, right? And relatively prime to n, means the GCD is 1. GCD of A and n is 1, right? So Z and the star is this set. Okay. So now there is an algorithm known as extended equilibrium algorithm that gives in B inverse for any B in Zn. So if B is in Zn star, we can find the inverse. Okay, using extended equilibrium algorithm. Because you see, if any element belongs to Zn star, it will have an inverse because GCD with of that element with n is 1, right? So we should be able to find the inverse. So let me first, so before describing extended equilibrium algorithm, I'll call it as extended equilibrium algorithm EEA. Okay, I will first talk about equilibrium algorithm. What is equilibrium algorithm? So equilibrium algorithm will find GCD of two numbers A and B. Okay. So how do we do this? We take numbers R0 as A and R1 as B. Then we compute R0 is equal to Q1 R1 plus R2, right? Where R2 is less than R1. R1 is equal to Q2 R2 plus R3, where R3 is less than R2. Okay. We are just dividing, okay, and so on. Then we have Rm minus 2 is equal to Qm minus 1, Rm minus 1 plus Rm, where 0 is less than Rm is less than Rm minus 1. Okay, and finally Rm minus 1 is equal to Qm into Rm. Okay, so I think this you already know equilibrium algorithm. I am just recapturing, recalling this modular arithmetic thing. So I can write a more precise way. In fact, you should note that GCD of R0 R1, which we want to find, right? The same thing, GCD of R1 R2, same thing as GCD of Rm minus 1 comma Rm. Okay, is equal to Rm. So this implies that GCD of R0 comma R1 is equal to GCD of A comma B, because R0 is equal to A and R1 is equal to B is equal to Rm. Okay, formally we can give you an algorithm. We are calling it algorithm 6.1. Here is the algorithm, equilibrium algorithm, right? Whatever I have written now in the pseudo form, R0 is equal to A, R1 is equal to B, initializing with M is equal to 1, while Rm is positive. We do these steps we are just doing, right? And finally we return these values. Okay, Rm is the GCD of A comma B. This is the pseudo algorithm for this. Okay, now I before defining extended equilibrium algorithm, I will give one result and one corollary which is important, because extended equilibrium algorithm, as I mentioned, is an algorithm for finding inverse of element B. So if B is an element in Zn star, extended equilibrium algorithm will tell how to find this inverse. Okay, one way is trial and error, you keep on checking, otherwise, or so basically you check if the GCD is 1 or not, right? So because this condition is there, the inverse will exist only if and only if. So B in Zn has inverse if and only if GCD of B in and N is 1, right? So basically, if there is an element B in here, how do we find the inverse? This is an important thing. So let me give you some result. Define two sequence of integers T0, T1, Tm, and S0, S1, Sm, such that Tj is 0 if j is equal to 0, 1 if j is equal to 1, and Tj minus 2 minus Qj minus 1 Tj minus 1 if j is greater than or equal to 2. Similarly, Sj is defined as 1 if j is equal to 0, 0 if j is equal to 1, and it is S of j minus 2 minus Qj minus 1 Sj minus 1 if j is greater than or equal to 2. Okay, so the result says that so once we define T0, T1, T2, Tm, and S0, S1, S2, Sm as per the following rule, we can say that this is our main result, theorem 6.1 from the textbook. For j lies between 0 and m, okay, we have Rj is equal to Sj R0 plus Tj R1. Rj's are as in algorithm 6.1. So proof I am not going to do it, but I leave it as an exercise for you by induction on G. For zero, what it does, input to this algorithm and is equal to R. So there exists integer S and T such that this happens. Okay. So anyway, now already 6.2. So R1 is 1. Then R1 inverse mod or not is equal to, so R that 1 T. This is given to us, right? GCD of R0, R1 is 1. So then Right? On mod R now good. Yeah, no, is is- is- well, the way. So I will so give uh, or it in pain as I think is and what this it uh see by I mean I I don't I thought when I well the in a two two no, well, this is in the value here for in that are my sent is once we just post low you low post low it's is like low but we oh the point so in some is and that So now we more know the uh, in uh, now I'm going to talk about Chinese Dementors theorem. This also you read in your discrete math class, so I am just mentioning it, or maybe I can do some calculations for you. Suppose m1, m2, mr are pairwise relatively prime positive integers. That means GCD of m1, mi, comma mj is equal to 1. You take any two pairs m1 and m2 or mi or mj and their GCD will be 1. And suppose that a1, a2, ar are integers, then the system of OR congruences like x congruent to a1 mod m1, x congruent to a2 mod m2, x congruent to a3 mod m3 dot 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 x congruent to ar mod mr. If these values are given, these equations are given to you, then this has a unique solution modulo capital M. Okay, and the solution is given by this quantity x is equal to summation I is equal to 1 to r ai capital Mi yi. What is capital Mi? Capital Mi is capital M divided by small mi, and yi is inverse of capital Mi mod mi. So I think we can see, suppose r is equal to 3, so there are 3 numbers, right? Suppose m1 is equal to 7, m2 is equal to 11, and m3 is equal to 13. Okay, so equations are something like x is congruent to 5 mod 7, x is congruent to 3 mod 11. Okay, and x is congruent to 10 mod 13. Okay, so then y1 I can compute these values, right? What is capital M1 from here? Capital M1 will be 143 capital M divided by small m1, which is 7 actually, right? By the way, what is capital M? So capital M will be 1001, the product of all three. From there we can find capital M1 143, capital M2 is equal to 91, and capital M3 is equal to 77. Right. So from here I can find what is the values of yi's. So y1 is 5, y2 is 4, y3 is 12. So x turns out to be this linear combination 715 into 5 plus 364, okay, into 3 plus 924 into 10 mod 1001. This simplifies to 13907 mod 1001 is equal to 894. Okay, so this is your Chinese remainder theorem. Now I think there are few more things that we would like to study, and which is sum of group theory. I think if you have done a course on algebraic structures, probably you might have read about them, but I'll just quickly recapture. So what is a group? So group is basically is a set together with a binary operation. Okay, a binary operation we can say star. Okay, such that it satisfies certain properties that for every a comma b in G, this implies that a star b in G close respect to star operation. Second, associative, for every a b c in G, we have a star b star c is equal to a star b star c. Third, for every a in G, so basically not there exists an identity element E in G such that for every a in G, a star E is equal to a is equal to E star a, right? And fourth, for every a in G, there exists a inverse in G such that a star a inverse is equal to a inverse a star a inverse a is equal to E. Okay, then such a structure is known as a group. So Zn is an example of such a group, with respect to addition, modulo n, right? So now there are certain other results. If number of elements in G is finite, less than infinity, then G is known as finite group. Okay, or so this number of elements is known as order of G. Okay, and if G is an element in G, we can define order of this element as smallest positive integer m such that G raised for m is equal to 1. Okay, then we have one important result known as Lagrange theorem. Lagrange theorem. It says that if G is a multiplicative group, this symbol is for multiplicative group. Okay, of order n, and small g is an element in G, then order of element divides the order of the group, which is n. This is known as Lagrange's theorem. Okay. Now we have one interesting corollary, which is if B belongs to Zn star, if B belongs to Zn star. So remember, Zn star is what? Is Zn star is all those elements A reduced to modulo n such that GCD of A and n is 1, right? If B belongs to Zn star, then B raised to power phi of n is congruent to 1 mod n. Now note that this is a result of very simple thing that Zn star is a multiplicative group of order phi of n, right? Because that is by definition. Zn star is all those elements A reduced to modulo n such that GCD of A and n is 1. And how many such elements are there? Phi of n. So Zn star is a multiplicative group of order phi of n, right? And hence we have this result that p raised to power phi n is congruent to 1 mod n because of Zn star is a multiplicative group of order phi n. Okay. So then we have another result or a small corollary known as Fermat's result, Fermat's theorem, which says that suppose P is a prime, okay, and B is an element in ZP, integer modulo P, then B raised to power P is congruent to B mod P. Why this is true? Proof is very simple, so I'm including it here. If P is a prime, right, then what is that? Phi of P is what? Euler-Torsten function phi of P. If P is a prime, then any number less than P will have GCD 1 with P, right? So all these numbers 1, 2, 3 up to P minus 1, how many of them are there? P minus 1, right? So phi of P is equal to P minus 1. Therefore, for B not a multiple of P, B raised to power phi of P minus 1 from the previous result is congruent to 1 mod P, right? From this result. And this means that phi of P minus 1 is P minus 1. So this will imply that B raised to power P minus 1 is congruent to 1 mod P. This implies that B raised to power P is congruent to B mod P, right? And if B is equal to 0 mod P, the result holds trivially, right? Then we have trivially 0 raised to power P is congruent to 0 mod P, right? So okay, I think now I can give you one more result. These results are very important for you to really understand. So let me do some more results. Okay. One more result is with respect to cyclic group. So if P is a prime number, ZP star is a cyclic group. You know what is a cyclic group? Cyclic group means, there exists one generator for it. So, which will generate the whole group. So in fact, in other words, this implies that there exists an element alpha in ZP star such that order of alpha is P minus 1 because the order of ZP star is P minus 1. So order of alpha is also P minus 1. So if order of element is same thing as order of the whole group, so that means that element is nothing but kind of a primitive element or generator which will generate whole thing. Okay. So that is how the definition is. Alpha is known as a primitive element. PE, primitive element. Okay, if order of alpha is equal to P minus 1. Okay, in fact, we have this result that alpha is primitive element mod P if and only if ZP star is nothing but alpha raised to power I 0 less than equal to I less than equal to P minus 2. So actually in this case, because it's a cyclic group, every element can be written as a power of alpha. Okay, so this is the main result. Let me give you some more stuff here, and then we'll do some calculations also. Suppose P is a prime, and alpha is a primitive element, mod P. Then any other element beta in ZP star. Remember, ZP star is all those elements A mod P such that GCD of A comma P is 1, right? Beta is some element ZP star, alpha is a primitive element mod P. Then beta will be some power of alpha, right? 0 less than equal to I less than equal to P minus 2, because alpha is a primitive element, remember? So that means every element here, if alpha is a primitive element mod P, all element of ZP star looks like this, power of alpha. Hence, beta is alpha raised by I, right? In a unique way. And order of beta we can define to be order of alpha raised for I, right? Which is P minus 1 divided by GCD of P minus 1 comma I. So thus beta itself is a primitive element, if and only if this denominator is 1. GCD of P minus 1 comma I is equal to 1. One last result, number of primitive elements. How many primitive elements are possible? That means there could be more elements, right? Is pi of P minus 1. This is a very interesting result. Let me show you an example. So, and then I will end the class. One example. Suppose P is equal to 13. Okay, it's a prime. So phi of 13 minus 1 is 12, right? Which is phi of 12, which is 4. So there should be 4 primitive elements. I mean, how do we find primitive elements? Let me just start with 2. One is not there, right? One is trivial thing. 2 powers 2 raised to power 0 mod 13 is what? 1. So I am just checking whether 2 is a primitive element or not. Okay. Then 2 raised to power 1 mod 13 is 2. 2 raised to power square mod 13 is 4. 2 cube mod 13 is 8. 2 raised to power 4 mod 13 is 3. 2 raised to power 5 mod 13 is 6. 2 raised to power 6 mod 13 is 12. 2 raised to power 7 mod 13 is 11. 2 raised to power 8 mod 13 is 9. 2 raised to power 9 mod 13 is equal to 5. 2 raised to power 10 mod 13 is equal to 10. 2 raised to power 11 mod 13 is equal to 7. So all of them are there, right? So that means 2 is a primitive element of primitive element mod 13. So ZP star. So Z13 star will have 2 as a primitive elements, right? Because it is generating a whole group, right? Okay, CP star is having 12 elements, right? So you can see that all 12 elements are here. In fact, what are the other primitive elements? So I think I can just use the formula to find out. You can check yourself by raising this power that they are primitive elements. Okay. So the element 2 raised for I is primitive element if and only if GCD of I comma 12 is 1. That means if and only if I is equal to 1, 5, 7 or 11. So the primitive element mod 13 are 2, 6, 7 and 11. So next is 6, another one is 7, another one is 11. So you just raise the power 2. So raise the power of 6, 7 and 11 and see that they are primitive elements. But actually finding primitive element is kind of tricky thing. I mean, it's a lengthy thing, right? You have to raise the power like here, and then find out. This can be simplified. I have a very small result I would like to mention, which is, the following. Or here I can mention one theorem. If factorization of p minus 1 is known, then this result can be used. Theorem 6.8. Suppose p is greater than 2, alpha is an element of Zp star. Zp star, remember, is all those elements A mod P such that GCD of A and P is 1. Then alpha is a primitive element mod P if and only if alpha raised to power P minus 1 divided by Q is not equal to 1 mod P. For all primes Q such that Q divides P minus 1. So if you can factor P minus 1, the result can be used to find the primitive element. Okay, so I think that's all for today. So next we'll meet in the CP building, CP102 in the next class, Monday 12 noon, right? And of course we'll be continuing the online things as well, but we'll be meeting it we'll meeting in physical. Okay, so we'll talk about RSA crypto system and the certain algorithms more. So I built the background today for all these things. Okay, any question? Okay, so I think I can end the session.